Well, first let's start with the outer layer. What's the derivative of arc sine of all this junk right here? According to the formula, 1 over the square root of 1 minus, and then what squared? All that stuff in here squared. So I'm going to write it down. It's the square root of x squared plus 1 squared. Yeah? That's just the derivative of arc sine of all this junk. Then chain rule says you come in here and you multiply now by the next layer in. So I've done the arc sine. The next layer in is the square root. So what is the derivative of the square root of something? Yeah, I'm going to put it over here just in case y'all don't recall. The derivative of the square root of x is 1 over 2 root x. That should be hardwired. Okay, that should be, you just throw that out. Now you can verify that just in case you're skeptical. That's the square root of x, right? Derivative of that, the 1/2 would pop out. You subtract 1 from a half, you get negative half. That's what that is. And then you could drop this down, and this would be 1 over 2 x to the positive 1/2, but then that's just 1 over 2 root x. So it's all the same. I would advise that you don't sit here and go and do all this. I would advise that you just memorize this. It just comes up too often for you to be doing this every time. So with that in mind, I'm now trying to take the derivative of the square root of this, right? So it should be, according to the formula, 1 over 2 root of, yeah, all the stuff that was under the root. So x squared plus 1. And I'm still not done, right? That's just the derivative of the square root part. Now I got to go in the root to the last layer, the x squared plus 1, and take the derivative and tack it onto the end with multiplication. So what's the derivative? 2x. All right, that's it. So I can clean that up just a little bit. I see some 2's going away here. I can square the square root. So I should get like 1 over root 1 minus x squared plus 1. Be careful you leave this in parentheses, because that negative would have to distribute. Then I have over here x over square root of x squared plus 1, because those 2's canceled. And maybe I could do a little more. How about we distribute that negative through? What would happen if you distribute the negative through? 1 over square root of negative x squared, because the 1's would cancel. Then you'd have times x over square root of x squared plus 1. And that's about all we could do with it algebraically. And maybe some of you are seeing a red flag. Anybody see a red flag? Yes, good. Do you see that we know that x squared is always a positive number, right? I mean, at the worst, it's 0, right? But any other number squared, we're going to get a positive number. Then I throw a negative in front of it. Then that's guaranteed to be negative, right? And then I take the square root. So if I ask you for the square root of a negative number, you're going to tell me what? It's going to be an imaginary number. Yeah? And that's a problem. Why isn't it being an imaginary number a problem? What's that? Yeah, look, we're just talking about real numbers, right? But that's, I mean, why are we only talking about real numbers? Well, because when you study Calculus 1, Calculus 2, and Calculus 3, we are studying functions of real variables. They don't say it right here on the front of the book for you, but it's understood that this is a course, this is a sequence of courses in real variable functions. If you want to start talking about imaginary numbers, then you have to take another class, and it's called Complex Variables. That's the name of the class. Complex Variables. And you usually cannot take that class until after Calculus 3 and after differential equations. It comes later on in the sequence. So any of you that are math majors will have to take this class, and what we do is we finally open the door and we say, welcome to the complex numbers come in, let's do calculus, but now let's use complex numbers. And it's a whole different universe of mathematics. But it's a great field because things that you would run into issues with here, you won't have to, I mean, you can work with them, okay? There's a way to deal with it. The reason we don't introduce it earlier is because in order to look at complex functions, you need 4 dimensions to visualize a function. So you know how I was saying, like, if you want to graph x squared, we can do it? Well, if you want to talk about functions and you want to allow complex numbers to be part of the game, then you have to have 4 dimensions to be able to see what's happening. And that's going to be a problem, isn't it? Because we can only really visualize 3 dimensions. So that's why it comes so much later, after the calculus sequence, after differential equations, because by the time you get to this, you're mentally, mathematically mature enough to handle things you can't see. Theoretically, that's what is supposed to happen, okay? So that's why we don't introduce it earlier. I have a really, really hard time in college algebra talking about complex numbers because I think it's kind of a crime. Because we just kind of look at you, we like kind of open the window and we say, look in there, and everyone looks in there, there's little eyes everywhere, and you're like, what the hell's that? And we tell you it's imaginary, and we shut the window and you never see it again. So I'd rather just not even show it to you, you know? And then when you get to complex variables, you deal with it. All right, so we have some problems with this, right? So the problem's over, we took the derivative, the idea is done. I put this here intentionally because I wanted to have a discussion about complex numbers to make sure you understood this class is not about complex numbers, and to also point out that you could have actually determined that there was going to be a problem with this derivative by looking at the function itself in the very beginning. It's because the x squared plus 1. What can you tell me about x squared plus 1? If I were to just graph x squared plus 1, what would it look like? Parabola going up, right? Right? Okay, what's the smallest value that could ever be? 1, right? And it's never going to be below 1. But in order to plug something in to an inverse sine function, you have to be between -1 and 1. And this inside piece is always going to spit out things that are 1 or bigger. Basically what I'm saying is that this is a really crappy function. It doesn't do anything. It's not defined except at one point. The only point that function is defined at is 0. I plug 0 in, I get 1, the square root of 1 is 1, arc sine of 1, we just did that a minute ago, is pi over 2. But anywhere else, you plug in any other x, that's an undefined function. So its derivative should have issues, shouldn't it? If the function itself's got issues. So I intentionally put that there just to point that out. It's a crappy designed function to begin with. All right, how are we doing? I've got about 12, 13 minutes. Are y'all doing all right? Y'all seem tired. It's 3 o'clock class, I guess. I have not taught a 3 o'clock class in probably, I'm guessing, 12 years? I don't think I've taught a 3 o'clock class in 12 years, easily. So I'm not used to being here this late. It's kind of weird. All right, now each of the other trig functions, right? I said all 6 of them have derivatives, and you should know what they are, not by memory necessarily, but you should know on your formula sheets where they are. And I believe the formula sheets that you can have on your tests are online in Canvas. I talk about this in the orientation. I believe it's 6 pages of formulas, and these formulas are formulas 19 through 24 on reference page 5. So know where to go to find them, all right? All right, next thing. Here's another derivative. Some more practice with chain rule. Find y prime given y equals root natural log of arctan of x. Now, I have not told you what the derivative of arctan is, have I? I told you just now it's in a formula, but I'm going to write it down over here. Because the derivative of arctan x, out of all the trig functions, out of all the inverse trig functions, this one is the one that you'll see the most. All right, this is the one that we're going to play with the most. So it's important that you recognize what the derivative of this is. It's 1 over 1 plus x squared. It's almost like the sine one, except there's no root and it's addition between those two instead of subtraction. So, I mean, I guess it's kind of like it. All right, so I see 3 layers again. Do you see 3 layers? See an arctan inside of a log, natural log, which is inside of a root. So starting from the outside, working our way in, the derivative of this should be, derivative of root of something is 1 over 2 times the root of whatever was in the root, right? The radicand, which would be all of this, right? So that will be natural log of arctan of x times the derivative of what? The natural log of this, which is 1 over tangent inverse of x. So the derivative of natural log of something is 1 over that something. Whatever that something is 1 over it. And then I continue. Now I go inside the natural log. The derivative of arctangent of x is 1 over 1 plus x squared. And I'm not thinking we can do much of anything to clean that up. So when I go through the homework solutions, if you go and watch me go through those to check as you're going, you'll see me get to answers like this, and then you'll see me try to manipulate them to make them look like the back of the book's answer. And you should go through the same exercise so that when you get to the test, you have some comfort level with simplification. Next one. This one's different. Why is this one different? It's implicit. Good. Because you cannot, it's not solved for y, right? It's not solved for y. And since it's not solved for y, you actually have to take the derivative on both sides with respect to x. So let's talk about the derivative with respect to x of the left side. And then we're going to have the derivative with respect to x of the right side. Maybe we'll start with the right side. I think the derivative on the right side is a lot cleaner and easier, so why don't we start there? What is the derivative of the sum of these two? Well, derivative of 1 is just 0, right? And what's the derivative of x times y? That's product rule. That is a product, right? And so you must apply the product rule. So I'm going to have derivative of 1, which was 0. And then when I do the product rule, it's going to be the derivative of this one times this one plus derivative of this one times this one. So what is the derivative of this one? 1 times y plus what's the derivative of y? dy dx or y prime times x. There we go. That's the product rule applied to the right side. And the 1, of course, dropped off to a 0. Any questions on that? Oh, I need to pass around the sign-in sheet. Your name should appear, and then you're going to initial. There's a really tiny box, so just initial in there next to your name, then pass this around, make sure it gets around to everyone. All right, so right side was pretty clean. Any questions here? Good? Okay, left side. Uh-oh. Well, I have chain rule. I have an outer function of arcsine. So what is the derivative of arcsine of this right here? 1 over square root 1 minus this thing, right? Squared? That's the derivative of arcsine of xy squared. Then I go inside this right here, and I need to take derivative of that and slap it on here with multiplication. But that is, again, a product rule. Very similar to this, except this one was xy, this one's xy squared. So it's going to be a little bit different when we take our derivative.
So you gave us one for your Monday, Wednesday class.
What?
You gave us one for your Monday, Wednesday class. It's printed off with 19 and 23. I mean 18 and 23.
Oh, I put, okay, just sign it. Sign in anyway. I'll check it. I'll change it. Thank you. At least it has your names on it. Okay, so since I'm going to have to do the derivative of a product and put it here, when you do product rule, you get two terms, don't you? Don't you? And I need to multiply this times those two terms. So I need to put a set of parentheses there. And now I go through the product rule. The derivative of x is 1 times the y squared plus, now careful here, derivative of y squared. 2y dy dx. 2y dy dx. So there's your chain rule. The 2 drops out, 2y to the first power. I don't need it, but I'll put it there. Then times the derivative of the base. The derivative of y is y prime. Now don't confuse the 1 with y prime. Okay, that's why I'm going to take it out of there. And then finish off the product rule times x. Look, there's nothing I've done here that's Cal 2, with the exception of this new derivative of arcsine is giving you this piece. The derivative of this, being this, is a Cal 1 topic, right? Isn't that? Okay. I know you had a long break, but I want to make sure everyone's on board with this. If you're not, you need to go back and review. All right, we have to get y prime, don't we? Okay, I'm not going to do it. I'm going to let you do it on your own, but I'll tell you what you would have to do. You have to take this entire thing and distribute it here and here, and that will create two terms, and it will actually free your y prime from this parentheses. Then you get all your y prime terms on one side of the equation, anything that does not have y prime on the other side. You factor a y prime out, and then you divide through. And I would just challenge you to go and try and do that on your own. If you have any trouble, in my class that I did this morning at 9, I actually finished it off. We had a little more time than we have here. So just go to my playlist. When you go to the videos for this class, just go to my playlist and you'll see 2414, Tuesday, Thursday, 9 a.m., spring class, and you can watch theirs. Now, I'm not done. I still have 3 minutes. I want to talk about the next problem. That's why I'm going to cut this one short. It wouldn't be a first day if we didn't do a word problem, right? Related rate. A rocket fired straight up with this a constant speed of 1,000 miles an hour. So you got this rocket that's flying up, right? Straight up in the air. An observer is a mile away, okay, watching with a pair of binoculars, right? What? Yep, not far. And so we'll put the rocket over there. It starts going up, and this person's got binoculars, and they're following the rocket as it goes up. The question is, at the moment that the rocket is 3 miles high, how fast is the observer's angle of inclination changing? In other words, how fast is their head rotating at the exact instant the rocket is 3 miles high? Now, this is a problem that you could have seen in a Cal 1 class, but somehow the section on inverse trig functions makes it easier, or we can do the problem using inverse trig functions and their derivatives. So let me take a minute to set it up, and I don't have a lot of time, so I'm going to do it quickly. All right, what we have here is a rocket. This is my rocket. That's my rocket. Okay, it's traveling at 1,000 miles per hour, right? Straight up like that. And we have an observer, which I'm going to look at as being a point on the ground. That observer is always a fixed distance of 1 mile away from the launch point of the rocket. I am interested in knowing how fast the angle of inclination is changing, right? I want to know how, if you start to take this point and start dragging it upward at 1,000 miles per hour, I want to know how fast that angle is changing at an exact moment that this is 3 miles long. So this would be like a general picture of what's happening. This would be a picture of what's happening at the exact moment that I'm talking about, right? Anyone else need to sign in? Okay, so I like to call this a general picture, and this is like an instant snapshot picture. And then I like to write down what I'm given, and then I like to write down what I want. So can anyone tell me Either of those, what I'm given and what I want, or what I want? I want d theta dt, don't I? I want d theta dt. I want to know how fast theta is changing with respect to time. And I want to know that when exactly the rocket's 3 miles high, right? That's, you could say it's part of the given too, but let me do something. I'm going to come over here. Do y'all agree this is always changing? Yeah. Let's call it a variable then, y. Then I want this when y is 3, don't I? I need to kind of, when you do these related rate problems, you have to kind of work with everything you've got. You know, go back to your picture, come back here. I want to know how fast the angle is changing at exactly the moment that that side y is 3. And I'm given something. I'm given what? dy dt. I know how fast y is changing with respect to time, right? I know how fast y is growing. It's 1,000 miles per hour. I know I'm out of time, and I hate to keep you here extra on our first day, but I think it's worth us finishing this up. All right, so we've got this, right? What we're given, what we want, when exactly we want it. The key now is to somehow come up with a relationship between theta and y, and you must use this picture. You cannot use this picture. So what is the relationship between theta and y? Any relationship you can find. Tangent theta is y over 1? Do you all agree that that's a relationship? Now, I don't have to put y over 1. I could just put y, couldn't I? All right? And that's it. We have an equation. If I take the derivative, you all tell me right now, what would be the derivative of tangent theta with respect to time? Secant squared theta d theta dt. It would be secant squared theta d theta dt. That would be the derivative of the left side. The right side? dy dt. So I'm taking derivative with respect to theta, with respect to t on both sides. Understand? Here's the problem. What do I know? I know dy dt, don't I? I want d theta dt. Good. But I also know y is 3. I don't know what theta is, do I? Now I could get theta from this. So I could still solve this. But watch how much easier, I promise, I'm done in 1 minute. Watch how much easier this is if I take this equation and instead of differentiating that, I take tangent inverse on both sides. What would I get if I do tangent inverse on the left? Tangent inverse of tangent of theta would just give me theta, wouldn't it? Tangent inverse of y would give me tangent inverse of y. Now differentiate with respect to time. What would you get? d theta dt. That's the derivative here. What's the derivative of arctangent of something? 1 over 1 plus here, y squared. But chain rule times derivative of what's in here, dy dt. And do you see how this one would be easier to work with? d theta dt, you know, use what you want to know. dy dt is 1,000, you knew that. And all you need now is y. And you have y is 3. And it's just easier. You don't have to go solve for the theta. Okay. Do your homework. See you Thursday. Sorry to keep you again. I apologize.
You were saying the thing about cell phones and stuff?
Yeah, let me turn off my camera before we...